Okay, let's get started. So in the last 2 weeks, we discussed format string vulnerability, which is different from stack-based buffer overflow. We started in the first half of the class. And in stack-based buffer overflow, we overwrite things on stack sequentially. But in format string vulnerability, with that percentage n or hn, hhn, we can overwrite anywhere in the victim process address space. So it's a very powerful attack. Today, we will study something called return-oriented programming, or simply ROP. I actually feel this is one of the greatest inventions in software security or software attack in the last 15 years. So today we will study this. So let's try to understand why ROP is so important and why it made such a contribution to this area, especially in attack. So far we already know that depending on whether the attackers need to inject binary code into the victim's address space, we can divide attacks into code injection attacks or code reuse attacks. We have seen a little bit code reuse attack. In some of the buffer overflow challenges, you overwrite the return address and that return address pointed to a function that is already in the address space. So you didn't really inject any code there, any binary, any machine code there. You only overwrite the return address. So you reuse some piece of code which is already in the address space. However, you also learned to put share code on stack, on the commands line arguments, in the environment variables. All of those are actually on stack. You can also put share code in other places as well. You already learned that. That is code injection attack, because in addition to subverting the control flow, you also need to inject some malicious code there. And share code is usually what we inject there, or now we call it share code. It doesn't necessarily return a share to us. So today, the return-oriented programming is a subclass of code reuse attack. However, we are not looking for a particular function in the address space. In the previous return to libc attack, we are looking for a complete piece of code, a complete function. That function print out a flag for us, right? But obviously, software developers, they were not conveniently placed malicious code for us in the address space. We cannot jump to that. And in return-oriented programming, we are going to generalize return to libc, and we are going to reconstruct wave gadgets together, chain gadgets together, to do arbitrary computation, to do something malicious. And those are just garbage and gadgets on the address space. Besides return-oriented programming, there actually are several other related approaches called jump-oriented programming, call-oriented programming, or even seek return-oriented programming. They are very similar, but they are not as easy as a return-oriented programming to pull off. Some of them has much more constraints, but the general idea is very similar. A little bit about the history of ROP. The technique, not a very generic version, was first introduced back in 2005. However, it didn't get much attention that time. And in 2005, someone come up with the idea to change the registers, to pass parameters to functions. Right? That's actually what we're going to do in the first challenge today. So recall that in return to libc, you usually need to set the parameter for the function you are returning to, right? So we did that for the 32-bit version because to set the parameters, those parameters were on stack in 32-bit. And we skipped that for 64-bit because 64-bit version of this system, we do not use the stack to pass the first 6 parameters. We use those registers. And when you do a buffer overflow, you cannot overflow registers. You can only overflow the stack. That's why using ROP, we can change the registers. And that is what this guy proposed back in 2005. Then in 2007, in ACM CCS, this is one of the big 4 security conferences. And in this conference, there was a paper called The Geometry of Innocent Flesh on the Bone, Return into libc without function calls on the x86. And this paper generalized the idea of ROP, and the paper actually coined the term return-oriented programming. So this is a screenshot of the original paper. As a homework this week, you are going to read this paper. And the author of this paper is Hava Shah-Chen. So when he published this paper, he was a professor at UCSD, and he published this paper just by himself. There was no student authors on this paper. Now he moved to, I believe, University of Texas at Austin. He graduated from Stanford. He made a lot of contributions to system security, ROP, including ROP, and also he made some contributions to crypto as well. So in this paper, he generalized this ROP attack, and in his own words, he said that in any sufficiently large body of x86 executable code, actually this is proved that for other architectures the same. There will exist sufficiently many useful code sequences, and those code sequences, in his paper, he called them gadgets, that attackers who control the stack will be able to weave them together, chain them together, to cause the exploit program to undertake arbitrary computation. So later you will understand what this sentence means. Looking at the title, the geometry of innocent flesh on the bone. So here the innocent flesh means those gadgets, those code sequences already in the address space. Those gadgets are not necessarily malicious. They were generated, emitted by compilers. They were benign, just code. However, if you chain them together, they can do something malicious, or they can do arbitrary computation, including something malicious. So 10 years after this paper was published, 6-7 years before now, this paper actually won Test of Time Award at CCS 2017. So that is the only paper won a Test of Time Award that year, I believe. So winning Test of Time Award, it's very difficult. It means that that paper influenced the security domain significantly. And actually, a professor in our department, Marilla Blanton, she also has a Test of Time paper award from CCS. I think probably before this paper. Yeah. In addition to that CCS conference version, there is a much longer journal version of the paper published in ACM journal TSEC. So TSEC recently they changed the name to TOPS, ACM Transactions on Privacy and Security. So if you want to learn more about this, you can read this more comprehensive journal version of this paper. Okay, so that's the history of ROP. Next, let's just learn how this works. How can we hack with ROP? So recall that in return to libc attack or return to any function attack, return to any function in the address space. If the functions we are returning to do not have arguments, so technically we can chain unlimited numbers of functions together, right? We had a challenge before, print out knowledge is power, fries is bacon. In that challenge, we have 6 functions. And we chain them together. We call return to functions one by one, right? So those functions, they do not have a parameter. None of those functions takes a parameter. And if we have more functions of that, we can chain all of them together. Unlimited numbers. The reason for that is at the end of each function, there is a return instruction. And that return instruction will pop the return address on the stack to the EIP. And then move the ESP up or RSP up, so they will not overlap with each other. In ROP, the only difference is we are not returning to a function. So previously we returned to a function. There is a function print fras. There is a function print is, right? Now we don't have those functions anymore. We just return to code sequences. And all of those code sequences, they have one thing in common, is they end up with a return instruction. So functions, they do end up with a return instruction, but there are more gadgets, code sequences on in the address space that have a return instruction. So in ROP, we chain the chunks of code, which we call gadgets. They're not functions. They can be functions, but they don't have to be functions. So those gadgets usually do not have a function prologue, epilogue. Sometimes they are very, very short. Just 2 instructions, a computation instruction and a return instruction. Sometimes it can be longer. It can be 10 instructions and a return. So we chain those gadgets together, then accomplish something much more sophisticated. And the gadgets, they are not necessarily stored in a continuous memory. They can be anywhere as long as they are executable. And they all end up with a return instruction. In jump-oriented programming job, they end up with a jump instruction or a call instruction, which we will not talk about in this class. In this class, we only focus on return-oriented programming. So the way we are going to chain them together is similar to how we chain functions together. We put the addresses on stack. So put the address on stack, the first return will go to the first gadgets. Then the first gadget has a return instruction. Then you will find the next address on the stack again. So it keeps, the stack pointer keeps moving up, and we keep execution the gadgets. So we do need to control the stack here. However, we don't need the stack to be executable. On the stack, we only have addresses. We can have some data there as well. Later, I will show you examples that we can have data there as well. However, we do not inject any code to the address space. However, here is a question. You may think there are only limited numbers of return instruction in the address space, right? You know that each function you implemented at least has one return instruction. If we treat those as gadgets, then there are just a number of functions of gadgets. Or maybe some gadgets can be longer, some gadgets are shorter, but seems like we don't have many. That is actually not correct. Because the return instruction itself on the x86 platform, they are basically just 4 different bytes. If you look at the binary level, bytes level, machine code level, it's just only 4 different bytes. It can be the ASCII value, the hex value C3, CB, C2, CA. That's it. That's only 4 possibilities for the return instruction. And they do not really have to be emitted or generated by the compiler as an instruction. You will see what I mean later. The x86 instruction set is actually very dense, and it can be variable lengths. Some of the instruction is just 1 byte. Some of the instruction can be as long as 13 or 14 bytes. Other instruction sets has similar characteristics. They are also dense. Some of the instruction sets, they are fixed size, like ARM, or usually RISC architectures, their instruction size are fixed, just 4 bytes, some of them are 2 bytes. However, x86 is different, right? Even if they are fixed size, there could be, we can also do ROPs there. It will be harder, but it's still possible for ARM because it can be either 2 bytes or 4 bytes, so it's possible. But for x86, it can be anything. So on our server, we already installed a tool for you. That's the ROP gadgets tool. Using this tool, you will find all kinds of gadgets for a binary. For example, here, I believe you don't have to use the Python 3 part because the script, I put the Python 3 there. You can say no job, means we are not into the job gadgets. We only look for ROP gadgets. Then we are looking for gadgets in this binary file. And this is a library file. This is a C library file. Then it will tell us all the gadgets and their location. And we can add an offset, the base location, to get its runtime location. Because when you run this one, obviously, you are looking for the offset of that gadget in this file. But if you want to know the runtime address, you need to add an offset there. So we disabled ASLR, so the base address here will always be the same. With ASLR, it will be harder, but still possible to attack this. There are many tools. ROP gadget is one of them. There is also ROPer and also Pong tools. Can find the ROP gadgets as well. In our server, I believe we installed the Pong tools and the ROP gadget. We will use ROP gadget, which is very straightforward. So how does those tools find the ROP gadgets automatically? So say here, let's say we have some byte sequence, right? Those are code. They have this value just byte by byte. So let's say if this is the assembly, this is what the compiler generated. The first instruction is increase EAX, and this instruction is only 1 byte, which is 40. The next instruction is exclusive or EAX, which takes 2 bytes. Then the next 5 bytes are one instruction. Let's move this number to EAX. So this may be what the compiler really generated, those 3 instructions. However, those 3 instructions, they map to this 8 bytes. And depending on, so you can say that here, there is no return instruction, right? The compiler didn't emit a return instruction here. However, in this intermediate value, there is a C3. And that C3 will be placed on memory, right? So if you interpret, the CPU interpret this piece of bytes not from the beginning. Let's say we've interpreted this from the 5th byte. Then the 5th byte will be interpreted as a store instruction. That hex AB will be interpreted as a store instruction. Then the next one, the C3, will be interpreted as a return instruction. So when you jump, when you do a return, you don't have to return to the beginning here. You can return to anywhere. If you return to the AB, then you are going to execute a store instruction, then a return instruction. That C3, which originally just data, now becomes the return instruction. Okay. And for the x86 instruction set, there are, because the instruction set is so dense, even if you have some random data, it can be interpreted as useful instructions. And because of that, it gives you many, many gadgets. For example, let's go to our server, and we just run a random challenge here. And what I'm going to do is I'm going to just get some random data from the Linux kernel using, let's do a cat device random. So this is just a Linux device that gives us random data. So let's put this into maybe a file. Let's put this random data into a file called R. So now generate some random data. Let's stop that. So let's take a look at that random data generated by kernel. We do a XXD. So I run that cat program maybe for 2 seconds, and the kernel give me that much of random data. Okay? So we maybe take a little bit of that random data. I here will interpret that using the C code format. So we just want to get maybe 20 lines of that, 30 lines of that. Okay. Even that's a lot. Did I do grep? Oh, I'm not. I'm trying to do head. Okay. So we get 30 lines of random data generated by the kernel. I just copy that. Okay, so this is random data generated by kernel. It's garbage. It's supposed to be uniformly distributed. We put this random data into a disassembler, and we disassemble that. And what's the result? They are actually valid instructions, because the instruction set is so dense. The CPU will believe they are valid instructions. But of course, you execute this, you probably will get a segment fault in the first several instructions, right? But you can say that. Some of them, the CPU cannot interpret, but most of them can be interpreted as valid instructions. That's how dense the instruction set that is. And because of that, it gives us a lot of useful gadgets. Okay, so now let's look at a concrete example. This is an example you should be familiar with already. This is overflow return 3. However, you only did the 32-bit version of this before, and today we're going to do the 64-bit version of this. Sorry about that. So we have a main function. The main function print out the print secret function's address, and there is a val foo. Val foo has a buffer overflow. There is a buffer. There is a gets. Gets get input from std in. Our goal is to return to the beginning of print secret in the 64-bit. So in your homework before, in 64-bit, you return to either here, print flag, or at the beginning of the print flag function. You didn't return to the beginning of this print secret, which means you skipped the check of I and J there in the homework. Okay. The reason to do that is because in the 64-bit, at that time, you don't have toolbox to overwrite I and J here. So now we're going to use return-oriented programming to overwrite the value of I and J, which are in a register, not on the memory, not on stack. So the 32-bit, we already know what the stack looks like. There's buffer. There's save the EBP, return address. 4 bytes higher than the return address. We have I and J, right? But they're on stack. However, for 64-bit version, I will be in the register RDI, and the J will be in the register RSI. And the buffer overflow you have here can only overflow the stack. It doesn't overflow any register directly. Okay, so this is what we are going to do here. Okay, this technique you are saying here, that's return-oriented programming, that's ROP. So this is 64-bit. Let's say the red part is our exploit. It's just data, no code. And this is what we're going to put on the stack. And this part is we have the buffer, which is 6 bytes. Then we have the saved RBP, which is 8 bytes. Then this is supposed to be the return address, right? Which this one is Wolf's stack. So the return address before overwrite is supposed to be the address of this one, somewhere in the main function. So now I will first give you the exploit here, then we try to understand why it works. In the return address of this stack, we are going to put the address of a gadget. That gadget has 2 instructions. It has a pop, RDI, then has a return. Those 2 instructions, that's it. So when this Wolf returns, it will return to that gadget somewhere and execute 2 instructions. One is pop RDI. So what is pop RDI? Pop is going to pop something to a register. Then it's going to pop the next item on the stack to the register RDI. And this is stack. This is where we control. Then we can put the value 1, 2, 3, 4, 5, 6, 7, 8 there. Of course, in this case, it's 8 bytes, not 4 bytes, right? So that pop RDI is popping this value into the register RDI. Then, because it's a pop, the RSP will move up 8 bytes, right? So RSP will point to next item. Then what is the instruction to execute next? It's a return instruction, right? Because the EIP points to the return now. Then what does return instruction do? Return instruction will pop whatever RSP points to the RIP. So the CPU start executing there. So what we put there is another gadget's address. That gadget will have also 2 instructions. We have a pop RSI, then another return. So after that return instruction is executed, this return instruction is executed, the RSP moves up another 8 bytes. And the EIP points to this gadget, which has the pop RSI and the return. So the next instruction to be executed is RSI, the pop RSI. And the pop RSI will pop whatever on the stack to RSI. And so we put data beef here. Then after that, pop, the RSP moves up, and we are going to execute the return instruction. And that return instruction will get this address to RIP so we can keep executing, right? So here, then we put the return secret functions address there. So after this, we are going to execute the function of print secret. But before that, we used those two gadgets to set the value of RDI and RSI. Does that make sense? So we're going to debug this later, so it will be easier for you to understand. So this is what our gadgets, our exploit look like, right? Very simple. Only each item is 8 bytes, so 40 bytes. 40 bytes here, and there is no shellcode. We didn't use any shellcode. We just reuse something on the stack. Okay, so I have a template here for you guys. You can copy this because you need to map those instructions to different address. So I feel this one is better if we have a template. In this case, let's say, so the buffer is 6 bytes. The saved RBP is 8 bytes. That's why at the very beginning, we have 14 bytes of garbage. Then we have each item 8 bytes. In total, we have 5 items here. The address of pop RDI return, then the first value, 1, 2, 3, 4, then the address of pop RSI return, then dead beef, then the address of print secret. Since those addresses could be different, that's why those addresses could be different. So we need to find those addresses in our server every time we run this. Okay, let's try. Let's go to challenge. This is overflow return 3. Overflow return 3. Overflow return 3 64-bit. Okay. So let's write the exploit here. Emacs window temp. Let's say exploit E. Oops. So that's our exploit. So we have 14 bytes. Then we are looking for the gadget address here, right? So if you go to the program, you use the ROP tool. You put the binary name here, binary buffer overflow. Then when you do this, you say if the program, the tool, let me close this one first. In this binary file we are trying to attack, the tool actually find us 78 gadgets. Some of the gadgets return end with a return instruction. Some of the gadgets end with a jump instruction or call instruction. In this class, we only care about the return instruction, so let's use no job here. It actually finds us 50 gadgets. You can see all those gadgets are quite short. only have several instructions, right? There is an AND, NOP, then return, then there is a pop, return. Those are the gadgets. And do we find the gadgets we want? We want the gadgets of pop, we wanted the gadgets of pop RDI and also pop RSI, right? So, actually there is a RDI here. Do we have a RSI? We actually find those two gadgets. Okay. So this one is not exactly what we want. We want to have a gadget of pop RSI return. This one actually has a lot of pop, right? Pop R15. But this gadget is also useful because we don't care about the value of R15. So we can put a random number there, then it will get into R15 and it will not influence the result, actually. However, there is another place we can look for gadgets, right? So when the program runs, the C library is also loaded in the address space. The program itself is very small. We only found 550 gadgets. But in the libc, there may be more. So how do we find the libc? We use the program LDD. Then we have our program here. Then it tells us this is the C library. There are actually other libraries we can also use, but the C library is big enough. This is the name of the C library, and the C library is loaded at this address. So if we do this, we use the same tool, rob gadget. We don't do a grep here. We look for all the gadgets in the C library, and we find out 20,000 gadgets here. Okay, so there are all kinds of gadgets for us to choose. If we only look for that pop RDI, we find many of those. This one is perfect. That's what we want. Then let's look for our SI gadget. See, this one is perfect. But however, the address here, you can see, this is a very small address, right? That's not the runtime address. That's just offset. That's why we need the base. We do a LDD again. We find the base. This is the base. Then this tool can compute the runtime address for us. Just do an offset here. Put this offset. This. Now we can find the runtime address of those gadgets. So the pop RSI gadgets is at this location. See? So now let's change our exploit. Yes. Now let's change our exploit. First, we look for a gadget, RDI. So use the command we just used, rob binary. This one we can just use. We can just use the program. We do a grep. Pop RDI. We find one gadget, and that's a runtime address. So we just copy that address, change our. There are many gadgets, the same gadgets. So we just choose one of them. So this is the address, the gadgets. Then we need to find another gadgets is a pop RSI return. We just checked. This program doesn't have that, right? This program has a different gadget. We're going to use this gadget later. Let's find that exact gadget in the C library first. So we need this offset. We also need this library's name. Oh, here is one. This is exactly what we want, right? That's a gadget's address. Then we put it here. We also need the address of print secret. So we do an M to be able to find the lemma. Let's say, where is it? Print secret. Let's do a grep. So that is the function address. Oops. So that's basically our exploits. That's the Python code to generate the exploits. The exploit has 14 bytes of garbage, then 5 items, each is 8 bytes, has the address of pop RDI, that value, pop SI, pop RSI, that value, then the print secret. So let's save this. Let's run this Python code. So when we run this Python code, when we run this, we get our exploits, right? 14 bytes of garbage, then those address. So if we pipe this into our program, we can get the flag. Okay. So now let's debug to step by step to say why this gives us the flag. Let's see, how do we do this? We don't really need those terminals. We just need one terminal. We just need one terminal here, then we debug this program. Then we're going to set a breakpoint at the valve foo first. Then we are going to execute with the input from temp E. So we are going to execute this Python script first. Then the output will feed into the std in of this program. So we execute this. Oh, there's null bytes? Why there are null bytes? Okay, there's a lot of way to do this. So we just put the to another file. Let's just put it to D. Okay. Now we debug this. We set a valve foo. Then we just run and use that temp D as input. Let's see. Okay, now it works. So the program runs, and we are at the beginning of valve foo. We haven't called gets yet. So let's set a breakpoint here. So after we have gets, we set a breakpoint, then continue. Now we just returned from gets. So now the stack of valve foo is overwritten by our input. Let's verify that. We exam. Let's exam 6 items from where RBP points to. What's wide? Giant, G, giant. Okay, so should be hex. Okay. So RBP supposed to point to what? The saved RBP, right? Which is 8 bytes. And we overwrite 8 bytes to A's. That's why you say all A's here. Then upper, we have an address. That's the address of pulp RDI return. Then higher 8 bytes, we have the value 12348. Then higher 8 bytes, we have another gadget's address. The first gadget we put here is actually in the program itself. That's why its address is so small. The second gadget we put here, the pulp RSI return, is in the C library. That's why its address is very high. Then we have the pulp, the dead beef. Then we have the function address of print secret, right? That's all we need. If you check more on the stack, then the other values, we don't care. We don't know what they are, and we didn't put them there. They were there in the first place. So now we are at the end of val foo. So let's do a NI next step to the return here. NI, another NI. Okay. So now we are at the end of val foo. We are going to execute the return instruction. So where are we returning to? Where are we returning to? We're not returning to the main function. We are returning to the gadgets, the pulp RDI return. Okay. So if we do one more SI here, you can see we return to the function libc csu init. We actually return to that function. So let's do an exam instruction, maybe in exam 5 instructions from where our IP is. And you can see that right now, the next instruction we're going to execute is a pulp RDI instruction. And the next instruction is a return. However, if you disassemble this program, you do not find those instructions here. Do you find them here? No, right? Here we're at address 13EC here. Where's 13EC? See here? The compiler didn't generate this pulp RDI return instruction. What the compiler generates was a pulp R15 return instruction. And obviously that pulp R15 is 2 bytes. However, the RDI is only 1 byte. And we jump to the middle of that. So if you go back here, let's try pulp R15, then return 64-bit. It will be what? 41 5F C3. Okay, C3 is that return. 41 5F is that pulp 15. However, if we have a RDI, then obviously it will be 5F C3, right? See? It's 5F C3. The compiler didn't give us a pulp 15. However, if we jump to that pulp 15 instruction in the middle, we get a pulp RDI instruction here. Okay. So now, if we execute this, then since it's a pulp RDI, the next data on the stack will be moved to RDI, right? So now, we are pointing to at a return, and RDI has already been changed. You can say RDI has been changed to the value we want, 1, 2, 3, 4, 5, 6. Right? Now we return again, and we return to now we return to our next gadget, which is pop RSI. Do the same thing. Then we can return to do the same thing. Then we pop the value to RSI. We do it again. Say now we finally return to the function print secret. But now the value of RDI and RSI are what we want. Like this. 1, 2, 3, 4, 5, 6, 7, 8. That's what we want. And also for RSI, it's dead beef. We successfully set both registers. And if we continue here, we will be able to print a flag. So in GDB, we cannot print the flag because in GDB, you don't have the root privilege. That's why GDB says it cannot open the file. However, outside the GDB, you will be able to print the flag. Does that make sense? Any questions so far? Okay, let's say, what if we do not have that gadget? Let's say we do not use libc. Only in libc we find that pop RSI gadget, right? Let's say we do not use that. We only use our own program. So we do not find a pop RSI return gadget. We find a pop RSI pop R15 gadget. Okay, how do we use this one? How do we change our exploit here to use that gadget? So the second one, the address here, will not be pop RSI returns address. It will be pop RSI pop R15 returns address. Then what else do we need to change? What? Put the garbage value where? Exactly. It actually should be after the dead beef, because the first instruction executed will be pop RSI. So the dead beef still goes to RSI. Then you put a garbage value there. Then the pop R15 will have that value, and we don't care about that value, right? Okay. So let's say how do we do that? We find the address here. Then we change our exploit. So after that dead beef, we have after the dead beef, we have 8 bytes of garbage here. So this next sign means this is little endian, Q means this is 8 bytes. That's it. Then we have it here. That's a gadget. So the gadgets, let me change this. The gadgets is not pop RSI, it's pop R15. Right? That's our gadget. So this dead beef will go to RSI. Sorry. This one, I need to change this address. This is the address. Then here, we only need some just garbage value, whatever. Right? Okay. Then this garbage value will go to R15. But when we call the function print secret, we don't really care about what the value is in R15. It's not going to affect anything. So that's our new exploit look like. All right. So if we run this one again, oops. something's wrong here. Let's say the address. The address looks, the dead beef, this one. Do you see any problem here? Looks like it's correct because this value doesn't matter. Dead beef, this address we didn't change. Okay, let's say this value is not changed. Okay, let's to see what we get. Oh, yeah, you're right. Here somehow I put the offset there because this one we don't need the offset. So all of the gadgets have a wrong address. Yes. So that's, it's supposed to be a small address anyway, yeah. That's the address we really need. Yep. Okay, so that's output. So that's our exploit. Then we pipe this into the program. And we also get the flag. So there are many different gadgets we can utilize, basically. Okay, I guess let's take a 10 minutes break. When we come back, we're going to say how we can use this to get the flag directly. Right now, we're still using that specific challenge where it has a print secret. Now, when we come back, we will check how can we use this to build something equivalent to our share code, which opens a file and sends file. We come back at 6:08. Okay. So we talked about the idea of return-oriented programming, the history, the basic idea. So now we are going to do something a little bit more complicated. So now I hope you get the feeling that what we are doing with ROP. Okay? There are benign code generated by compiler, like Yoda. Then we try to find pieces of those gadgets. We break them down, find smaller Lego pieces, then we chain them together, reassemble them together, and we get a Darth Vader here. So obviously, it can be the other way around. It can be malicious code, and you use ROP and ask it to do something benign, right? So there are some useful gadgets I will briefly mention. So if you want to skip data on the stack, you can just use a pop gadget, like just now we use the pop 15 there, which we do not really use 15, but then we skip data on the stack, and that gadget was the only one available to us. Also, if you want to have a lob sled, like you had in your shellcode, you can just find simply return instructions. You just keep going to that return instruction, so the ISP keep moving up, and you don't really do anything. So you can also build something similar to a lob sled using simply the return gadget. And the return gadget is anywhere. You just need a C3 somewhere, right? Also, you can pivot the original stack. If the original stack is very small, if there is a stack calorie that you cannot really, no, not stack calorie. Let's say you can only overwrite a small portion of that original stack. Then you can use a gadget like this, exchange RAX RSP. Then you exchange the value, swap the value of those two registers. Basically, you change your stack to some other location, and you can control that location. That could be another address. You can put a lot of data there, so you can pivot the stack as well. So there are many things you can do with this approach. Of course, a lot of very useful gadget will be the system call instructions. However, it's very difficult to find system call instructions in a program. There are not many because the C library will have some system call instructions for x86, for 64-bit. However, those system call instructions doesn't have a return, right? You need a syscall return. Those are hard to find. Actually, this tool, the ROP gadget, it has a feature to generate an exploit for you. Sometimes it has errors, but it has a basic idea there. You can try. It's not always reliable, but sometimes it works. So next, we are going to do something more generic. Instead of attacking that specific challenge, we'll attack a more general challenge, the overflow return 4. And we're also doing 64-bit version of this, and the stack is not executable. So previously, when you do this one, the stack was executable because you put shellcode there. Now we don't put shellcode there, and we're not using 32-bit. And in this program, there is no print secret function for you. Okay. So we're going to build a ROP chain, and this ROP chain does the same thing as our 64-bit shellcode does. It will open that flag file, then print it out. So we're making several system calls, at least two. The first one is open. The second one is send file. However, like I said, we are not directly using the system call gadgets because we cannot find those gadgets. So instead, we are going to call 64-bit C library function instead. So this is what, where do we put all the values in the register? The first, because the system call will also have corresponding function call, right? So there is a C library function called open, which eventually makes a system call to the system call open. So making the system call here is the same as making the function call. However, the system call doesn't have the return. The function call have the return. So we're going to call the function call C library function open, and we need to put the first parameters in RDI, the second parameter in RSI. That's our first function call. The return of that value of that will be the handler or the file descriptor of that file, and that one will be the second parameter of the second function call send file. So the return value will put in RSI again, and the first parameter for send file will be file descriptor 1, which is std out. So we put that one in RDI. Then the index in that file will be 0, so RDX will be 0. Then RCX will be how many bytes we want to output. We can put 1000 there, but you all know that the flag file we have, it's not really that long, so maybe 100 will be enough. You don't have to put 1000 here. Okay. So that's basically how we are going to call this. So this is the same as how we develop the shellcode. Then the stack will look like this. We will have the buffer, saved RBP. Then we have some gadgets to set up the registers. The register of RDI SI. Then we have the address of open64, which is a C library function for the system call, the wrapper of system call open. After that, we are going to set up the registers again using then return to send file 64, right? So to set up those registers, we are going to use those ROP gadgets to set up the registers. Okay. So let's say this is source code. You already said this many times. Main function calls valfoo. Valfoo has a buffer. C level 30 bytes, then the gets. That's it. The stack is not executable. However, there is no stack calorie in this one. So this is a template we are going to use. We have looks quite complicated here, right? I think the last one we don't have to use, I believe. Yeah, the last one is probably exit. Yeah, this is 60. So last one I use a syscall. I didn't use a function call. This one is exit, so technically we don't need this part. We only need from the beginning to here. So let's take a look at this. Because some part of this is a little bit tricky. So the first gadget we have here will be pop RDI return. Hold on, this one. I should change this one. This one should be flag. Pop RDI return. Then we put the data's address into RDI. Then we pop RAX. Something is wrong here. I think this is my older version of exploit. Let me see. So this looks like an older version of exploit here. Because the older version, I needed the memory to do that. But the new version, I think I don't need the memory anymore. Let me see. The first instruction is pop RDI. So the data's address is popped into RDI. Then next we will pop RAX. Then we have the flags address to RAX. Then we move that flags address to this memory location data. Then we have the pop RSI. Then pop RSI is 0. Then we have open 64. So why do we need that data again? So older version, definitely we need that data, but looks like now we don't need that data. Yeah, I think this can be simplified actually. Yeah. So anyway, the first part is we're going to set up RDI and RSI. It will be simpler than this because this can directly pop into. Oh, okay. There are several different ways to do this. We can place that flag string on a environment variable, so we know where do we have this flag string there. Here, what I'm trying to do is actually get the address of flag string. So the first step, I find a writable memory location, and I use the dot data section because in the address space, the dot data section is readable and writable, right? Even though there could be some important data, but I don't care about that data. I just find that address, and I'm going to save that address into the register RDI. Next, we put a string /flag here. However, this string is on stack, but I don't know its address, right? I don't know its runtime address. This program doesn't tell me where the stack is. I can put a string on environment variable so I can find address, but here I didn't do that. I put a string there. I don't know its address, so I did a pop RAX here. So I pop the string itself, not the address of string, the string itself into RAX. Because the string here is only 5 bytes, 6 bytes. The RAX is 8 bytes. Then I find a gadget to move whatever is in the RAX to the memory location RDI. The RDI points to the data section. So I basically move the string flag to that memory location. The reason I need to find the data section is I need to find a safe place where I can write. If I just find an arbitrary place in the address space, when I write to that, I may crash the program, right? That's why I use the data section. So after we put the string there, then we know that string flag where it is. It's where RDI points to, right? Then RDI basically points to that string flag. Then I pop RSI, and in this case, RSI we just set it as 0. Then we have the address of open 64. Now we then we return to the function open 64. That's basically the first part of this exploit. Like I said, this part can be simplified a little bit, streamlined a little bit here. So if we put the flag in the environment variable and put many copies of that, we don't need to move it to the data part, the data section. Okay, we can save probably 2 instructions there. The second part of the exploit, what we do is we're going to set the return value of open, which is in RAX, to RSI. But we actually already know that value will always be 3, right? Because this program, when it runs, it will have the std in, std out, std arrow that takes file descriptor 0, 1, and 2. So when we do this open, we will have the file descriptor 3. So to make it easier, we don't have to set to use that return value, which is hard code 3 there. Then we need to set RDI as 1, then RDX as 0, RCX as 1000. Yeah, that's it. So we have many bytes, then we look for those gadgets. Then a gadget I found here this is a long gadget, but it can do what we want. It will move RAX to RSI. See, that's what we want, right? RAX has a value, return value of open. We move that to RSI. But like I said, to simplify that, we just use 3. The byproduct of this gadget is it has so many other things here. And those things may crash the system, so we need to be careful. So here, if we set the ECX to 0, it's not going to execute this part, but this is a repeat and moving, right? Then after that, we have the pop RDI gadget, then we have 1 here. So we change RDI to 1. Then we only need to set RDX and RCX. And so we have RDX here. RDX is 0. We do not find a RDX return gadget. That's why we have a pop RDX, pop R12 gadget here. Then RCX, did we really change it? We probably didn't change it because, we do change it. So there's another gadget, pop RCX here. And here I just use 80. I didn't use 1000 because the flag is not that long, right? Then we have the send file 64 function address. That's it. We don't need the last 39. So that is our what our exploit looks like. We can simplify this a little bit. Does this make sense? Okay, then let's try this. Let's try to simplify this. I think we can find easier gadgets to use here. Overflow return 4 64-bit. No execution. Yeah, that's right. So this is our exploit. Let's say the first one is pop RDI. Let's remove this. So this part we don't need. We just find the address there. Okay, this part we can remove. We don't want this part. Makes it much easier. And also use simpler gadgets because to use this one, I find a very complicated gadgets there. So we don't even need the flag string here anymore because the flag string will be on stack, right? So here we just need the address of string flag or / flag, doesn't really matter. Flag will be simpler, I guess. So we put this address here. So when we do this pop, this address will pop into RDI. Then we just do a RSI. Then we do open, okay? So this one we can also make it simpler. Instead of having, the only reason we need this big gadget is use the first instruction. But we already know that the value will be 3, so we just do a pop RSI, right? Just do a pop RSI return. That will be our gadget. after that, we will put the value 3 there. Three, that's the file descriptor. That should be 3. Then DI will be 1, right? So DI is 1, this one is 3. Yeah, I think it's much simpler. Then DX is 0. RCX, here we set 50 in hex, which is 80, but that doesn't really matter. 40 should also be okay. Then we have the return address of send file. Then the last one is exit, doesn't really matter. So, okay, looks good. Let's verify that value 56 is correct. Here we have the value 56, which should be the buffer size plus 8 saved RBP, right? Let's verify that's correct. BJ dump. So vol here is RBP minus 30. 30 is 48. 48 plus 8, 56. That's correct. Okay, so this part is correct. So now we just need to find the gadgets of those gadgets. Okay, so now we should have 2 terminals, easier. So the first gadget, so we'll do ROP binary. I would directly go for the C library for the gadgets because there are just more gadgets. So then we need the offset. We have, what else do we need? That's it. That's how we get the address and gadgets. Yeah, that's how we get the address and gadgets. Then we just look for the gadgets we need. The first gadget is pop RDI here. Oh, there are so many. Maybe we can directly find the RDI return. Okay, we find one. So here is a pop RDI return, exactly what we want. That's the address of the gadget. Go back here. The next, we need the string, the address of the string, right? So like we said, we put this into the environment variable. So we do what's the name of that? How do we do that? Set environment or export? Okay. Export. Just a string. So how I do it? Forget. No $sign, right? $sign, okay. So we put, okay. So then we put Python 2. Since we are executing in the root directory, we don't really need the slash there. what's the syntax again? Print. Dash C what?
Dash C and then print.
Dash C then print. Oh yeah. Dash C print. Yeah. Okay. So maybe we do 1,000 of those. 500 of those will be okay. Oh, we also need a 0 byte there because it's a string, right? So we need a x00 like this. How did we do this before? What? No, but at the end we will need new line will also work maybe. So previously we were doing a lot of slash. Oh yeah. We were doing a lot of slash, and the new line there will be automatically a new line, so it doesn't really matter. Okay, so we do 500 of this plus this. Okay, then let's print. Okay, that's correct. Okay. Then we just get the address of that. Get environment variable 64, then string. So now it gave us address. Maybe 500 is not enough. Let's get bigger, much bigger. Okay, this address. Now we have the address of the string. So here we have 7B. Let's just change to BB. Should do it. Now we need to find the next gadget is pop RSI. Good. Final. Find exactly the gadget we want here. Now we have 0. Now we need to find the address of open64, which is a function. Then we can just GTB this program. Then set a breakpoint main. Then we print open64. Huh? We don't have that? Oh, I didn't run it yet. Run it. Now we print open64. So that's the libc function open64. That's the address we need. So we do have another function, so let's find it. Yep, that's correct. We do have another function, is a send file. Send the file 64, which is this one. So now we change send files. This address. Just make sure it's correct. Okay. So this one pop. Oh, this one we need another pop RSI, right? Not pop RSI. So basically we can reuse the address of this gadget because we already find the gadget address. That's the same gadget we want, pop RSI. So do it here. Then file descriptor 3. Then we need another pop RDI gadget, and we will have it. This address. Then 1 for the std out. Then we need to find this pop RDX gadget. I think we don't have that gadget. That's why I find a pop RDX and pop 12 there. Let's see. We're trying to find a pop RDX. Pop RDX and return. See, we do not really find this one. This one may work. But this one there is a return with some number. That will change the stack. So this one we also need to put some garbage on the stacks here. So let's say instead let's find a simpler one. So here there's one pop 12. We can also use this one. RBX, because we do not use RBX. Let's stick to our plan. RDX, pop R12 there, then return. Okay, then RDX we're set at 0, that's offset. Offset in the file. Then R12, doesn't matter, just use 1 there. Then we need to find our gadgets, pop RCX. Okay, we find one gadget here. RCX. You actually see that the least significant bytes, they are the same, right? So 822. So which means last year I was using those addresses, but because we turn on and turn off the ASR, so it has a different address. Okay, I think that's it. So this one is 80, that's enough. So this one already changed. Send file 64 we already changed. Last 3 don't matter, that's the exit. Okay, I think it should work. Let's oops. Okay, this is actually the first time I streamline that, so I hope it works. I haven't tested this before. So that's our script. Let's try. If it doesn't work, we just debug. Segment fault. Okay, something's wrong here. So let's debug to find out what is wrong. Let's put it in a file here. Then we do GDB. We have a valve. We run this. Temp D. So we basically want to get to the end of this. We continue. Now we are at the end of. Now we are at the return. So we are supposed to return to our first gadget, RDI, right? Let's say if it has what we want. We examine 5 instructions at where our IP is. Okay, so it looks correct. We have RDI, we have return. We just need to check if the value is correct. Do it again. Now we are at our next gadget, but RDI should have the address of that string. So let's print RDI. Oops. So that's here. We're supposed to have that string flag. So let's examine that, whether we have that string. Maybe the problem. No, we don't have that. Oh, I should not use the star. We don't have that string. Oh. That's because we set the string on the left-hand side terminal, and we had the right-hand side terminal running, so that we don't have the string here. Okay. Okay. How do we do this? So we have to exit here. So I guess we have to exit here. Okay, let's see if that environment variable is still here. Okay, it's here. Then we create a new terminal. Okay. So now in this terminal, we try to see if we have that environment variable. Now it should have that. Don't have that. Oh, it don't have that. Okay. So we do have it here. So even if we create, I did use export, right? Did I? I did use export. Okay. Let's even get all of this. So do we still have that? Get 64 string. Nope, it's not here. So we need to set that again. Export. Huh, that's weird. Export should work. Anyway, we set it here. Python 2. Print. 2,000 times. Plus flag. Okay, looks correct to me. Let's verify this. String. Okay, looks good. Now we get the address again. Then we just change the exploit again. So exploit. Six F. Let's use FF. Those zeros don't really matter. Just want to look better. Okay. Let's try again. Temp E. Yep, it works. Okay. So now we get a flag. So I just streamline that. It's simpler than the exploit I have in the slides. The exploit I have in the slides is more generic because it doesn't require you to set the environment variable. You put the flag string to a place we know where it is. Then it also try to get the return value of open. However, this gadget is really hard to find. I think I only find one gadget to do this, to move RAX to RSI. Of course, there may be other gadgets to move RAX to another register, then from another register to another register, eventually move to RSI. That should work. But I did find this gadget. However, the gadget has two more instructions. So when the ECX is 0, those two instructions don't do anything, so there's no side effects there. Okay, that's basically all I have today. Any questions so far? Kyle, you have a question? Okay, so the homework today, only two challenges. just to replicate what I did in class. You can make this piece of exploit work, or you can streamline it like what I did just now, and also have the previous example to set the RDI, RSI. In the final exam, there will be a ROP challenge, just the one ROP challenge. So make sure you understand how this one works. Okay, that's it. Then I guess happy, what's the holiday? Halloween? Thanksgiving, okay. Okay, happy Thanksgiving. Next week I will be out of town, so I will deliver the class online next week. Okay, see you guys in 2 weeks.